Hey geometry, we're still talking about dilations, and today we're going to talk about dilations that will map rays, lines, and circles. And just like I said the other day, this does not mean a map to get from Fayetteville to Springdale. It's mapping like we've done with all of our transformations. Opening exercise: is a dilated ray still a ray? If the ray is transformed under a dilation, explain how. Excuse me. Ray. If I have a center O and I dilate it, that was supposed to hit that spot. So this would be like ray AB. I dilate it. Okay, you weren't supposed to have to see that there. I'm just trying to follow my line across to make sure it's parallel. Okay, it's still a ray. It's a dilated ray, but yeah, it's still a ray. So if the ray is transformed under dilation, explain how. Okay, I just sort of showed you how, but we're going to do it a few more times during the lesson. So now we're going to dilate a little nicer. Dilate ray PQ by a scale factor of 2 from center 0. So we have ray PQ. This is in your classwork. PQ, and the ray goes through Q and continues. I drew, sorry, this was point O. I drew lines outward, measured O to P, doubled it, P prime. Then I measured O to Q, doubled it, Q prime. Connected my dots, drew the ray through, and I have my dilated ray. Pretty simple. So, is this figure P prime, Q prime a ray? Yeah. A dilation of PQ is, dilation of ray PQ is ray P prime, Q prime. How, if at all, has the ray PQ been transformed? So, the segment in the ray, actually I'm going to do it this way, sorry. The segment PQ in ray PQ is twice as long. As the segment PQ in the ray PQ. Okay, the segment has increased by a scale factor of 2. Will a ray always be mapped to a ray? Yeah, I can't come up with a reason why not. The definition of dilation says that your new figures are similar. Angles are always congruent. But yes, a dilation of a ray will always be mapped to a ray. Okay, so example 1. Will a dilation about center 0 and a scale factor of r equals 1 map PQ? This would be ray PQ. Will it be mapped to P prime Q prime? If we have our center and we draw our rays out, what if I have a scale factor of 1? If I measure this, well, I can't I can't double it, I can't half it. It's a scale factor of 1. So a scale factor of 1 means that the ray and its image are equal. So the dilation doesn't enlarge or shrink. The figure remains unchanged. So a scale factor of r equals 1, the dilation maps the ray to itself. Okay, example 2, I drew a picture. The line that contains ray PQ, right there, does not contain point O. Does a dilation D about a center O and a scale factor of R not equal to 1 map every point of PQ onto a point P prime Q prime? So, this is a problem we're going to be seeing for the next 3 examples. And all we see is, like, what we're trying to get to here is if R, is a point on ray PQ, then is the dilation of R a point on P prime Q prime? Okay, that's the question we're really asking. Also, oh, for goodness sakes, there we go. Also, if a point S prime lies on the ray P prime Q prime, then is there a point S on the ray PQ such that the dilation of S equals S prime? Okay, so that's the question we're really looking at. Okay, we're going to look at, we're going to examine scale factors greater than 1. Between 0 and 1 is a similar discovery, a similar proof, but we're only going to look at scale factor greater than 1 today. Okay? All right, so we're still using the same diagram. We know this relationship here. I have OP and OP prime. Okay, this is the splitter theorem, OQ and OQ prime. We know that from what we see here, that OP prime over OP is equal to OQ prime over OQ. And that's going to be equal to our scale factor, right? That's the triangle side splitter theorem. And from that theorem, we can say that the segment PQ splits triangle OPQ proportionally. So PQ splits triangle OPQ proportionally. We can also say that the lines that contain, can't spell, the lines that contain ray PQ and ray P prime Q prime are parallel. So we know that PQ is parallel to P prime Q prime. Line PQ is parallel to line P prime Q prime. Therefore, we know ray PQ is parallel to ray P prime Q prime. Cool? All right. Let's take it one step further. Okay, we introduced the dilation theorem. I think that was last lesson. And if we talk about that a little bit, just to reinforce what we're learning, if we talk about the dilation from O of the segment PQ is the segment P prime Q prime, right? So we can write it in function notation. Dilation of PQ equals P prime Q prime. So the dilation of segment PQ is equal to segment P prime Q prime. So we only just consider some arbitrary point R on ray PQ that lies outside of segment PQ. So what we're really looking at is a point R. Let's just say point, I know I'm highlighting now, a point R on ray PQ. So we can just say right here, a point R on ray PQ that lies outside of segment PQ. Okay, so for any such point, what point is contained in the segment PR? Okay, that's just another random question. Okay, let's write that down so you can see it. For any such point R, what point is contained in PR? Okay, the answer is point Q. All right. Okay, let's look at the next slide. Okay, that's what we just talked about. I have point R here, and I said in the last slide, for any such point R, what point is contained in the segment PR? Well, point Q is right there. Okay, so here I can say let R prime equal the dilation of R. Okay, with the dilation theorem, if we have the dilation from O, the segment PR is segment P prime R prime. So dilation from O, we have PR, the segment PR is the segment P prime R prime. Okay, also by the dilation theorem, we know that the dilation of Q equals Q prime. And Q prime is a point on what? On segment P prime R prime. Okay, dilation theorem tells us that too. Therefore, P prime Q prime, the ray, and P prime R prime, the ray, must be the same ray. And they are. We see it right here. PQ is the same as PR. We can name it either way and it wouldn't matter. Okay, in particular, R prime is a point on P prime Q prime, which is what we needed to show. That was the goal here. R prime is a point on ray P prime Q prime. Okay. All right. So let's try to wrap things up. To show that for every point S prime on ray P prime Q prime, there is a point S on ray PQ. And that's such that the dilation of S equals S prime, right? Now, consider the dilation from center O with a scale factor 1 over R. This is one of your problem set problems. That's the inverse of dilation D. the dilation maps S prime to a point S on ray PR. Okay, we just went backwards. So by the same reasoning of above, the dilation of S equals S prime. And if it's 1 over R, which your scale factor is between 0 and 1, then it's going to go from S prime to S. Okay, and I think that is a pretty good conclusion. Example 3. The line that contains ray PQ contains point O. Does a dilation about center O and a scale factor R map PQ to P prime Q prime? So we're going to actually get this question for the next 3 parts. This is part A. Examine the case where the endpoint P of ray PQ coincides with the center O of dilation. So those are the same, right? If the endpoint P of PQ coincides with the center O, what can we say about ray PQ and ray OQ? So what can we say about ray PQ and ray OQ? What can we say about those two things? I've copied a picture in. I don't believe this picture is in your classwork, but you can sketch it in if you'd like. Basically, we know all the points on PQ also belong to OQ. So PQ equals OQ, right? That's what this is. So by definition, a dilation always sends its center to itself. So I know that O equals P equals O prime. I don't know why I wrote Q equals P prime. Okay, let's get to the next page and I'll try to explain it further. So we see here, excuse me, the same drawing with an X written in it. So let X be a point on ray OQ, so that X isn't equal to O, okay? What happens to X under the dilation about O? Okay, what happens to X under the dilation about O with a scale factor of R? Okay, we can look at the scale factor greater than 1 and a scale factor of less than 1. So for this one, we see that OX gets dilated to OX prime. So the dilation sends X to X prime on ray OX. So really we see that OX prime is equal to the scale factor times OX, right? Same here. We see that, let me highlight it, OX prime, sorry, that's OX, and this is a scale factor less than 1, goes to OX prime. And it's the same thing. OX prime is equal to the scale factor times OX. So we know that OX and Q are collinear. So OX prime and Q are also collinear. Oops. And X prime is on ray OX, which coincides with ray OQ. Awesome. Let's look at example B. So here we have the same beginning statement, but now we're going to examine the case where the endpoint P of PQ is between O and Q. on the line containing OP and Q. Okay, so I drew a little picture. Well, no, I didn't draw the picture. I copied the picture. We already know from the previous case that the dilation of OQ maps onto itself. So the dilation of the ray OQ maps onto itself. All we need to show is that any point on the ray that is further away from the center, be it P, any point on the ray that's further away from the center, then P maps the point that is further away from the center, P prime. Okay, so examine the case where endpoint P of ray PQ is between O and Q on the line containing OP and Q. It's just going to map further out or further in, depending on your scale factor. All right, let me show you another example. So here we have lines where I've added an X. Here I know that OP is going to be less than OX just because of where I placed X. So when I scale, I'm going to have OP prime and OX prime to compare. On this first drawing, I have OX and OP. And as I stated, we know that OP is less than OX. On this second drawing, I also have OX, which when your scale factor is greater than 1, maps to OX prime, and then OP, which my scale factor is greater than 1, maps to OP prime. We still see that OP prime is less than OX prime. And what we just did is I had OP, R times OP, is less than R times OX, which is the same as OP prime is less than OX prime. So I just multiplied both sides by R when R was greater than 0, and that's what it gives me. Okay? That's when R is greater than 1. Cool. All right, example 5. Does a dilation of a center O and a scale factor R map a circle of radius R onto another circle? Okay, first of all, we look at the case where the center of the dilation coincides with the center of the circle. It's just going to dilate out, sort of like an eyeball would, the center of your eye, the black part, the pupil, there we go, would dilate in and out when it looks at a bright light. So, I mean, I just measured the radius here, and then I went out again. I guess I drew a ray first. I took my compass and measured this and went again and then drew a circle all the way around. The hardest part is always drawing the circle. Part B, examine the case where the center of dilation is not the center of the circle. We call this the general case. So that would be my center of dilation, and this is my circle. And on the next slide, I'll show you how it dilated, which was a lot of fun. Hopefully you can see how this evolved. I had the circle. I added some points in here just to help me with the dilation, because it was hard to dilate the circle without more points to mess with. So I just drew some random radii out to the sides, P, Q, R, S, and T. That C is just the name of the circle. So I drew rays through each one of my points, right, all the way out. And then I measure from the center, which is D, out to the points. And I think it was a scale factor of 2. Well, I used a scale factor of 2. So then I went from R out to R prime. You'll see I went from D to P, and then P to P prime. That's the only one you see. But here, you see them all. Okay, all of these. I just doubled the length, and I even doubled the center, because when I use my compass, that's where I'm going to put the pointy end, right? Then I put the pencil out here, and it should draw all the way around. Here's where I put the pointy end at the center, and then I drew the circle all the way around. And you see, it's not perfect. I mean, there's always some margin of error when I'm drawing things by hand, but I drew the circle all the way around. I tried to erase most of my points so that it was clearer to see. That's it. Sort of a long video, but just a lot of explanation. I hope most of it made sense, and tomorrow when we do our problem set, I hope to cement the ideas in your head. Good job today.